Hi, my name is Ty, and today we're going to talk to you a little bit about waves. Many vital and daily objects and electronics use waves, such as phones and wireless computers and many other things. And then some different types of waves. They include light waves, radio waves, X-rays, and sound waves. And overall, to get a better understanding of what the definition of a wave is, before we go in depth with it, a wave, the definition of it is a disturbance of matter that carries energy. Now, it is very important to notice that waves move energy, but not matter. And then the next drawing, I'm gonna show you a picture of a drawing that I created with that has certain vocabulary words or properties of a wave that it's important to get familiar with before we go more in depth. Alright, so as you can see, the equilibrium position is the center of the wave that separates the crest and the trough, or otherwise known as the top of the wave from the bottom of the wave. And to get a better understanding, the trough is the lowest point of a wave below the equilibrium position. So as you can see, I labeled it, it's the lowest point. And then the crest, on the other hand, is the opposite. The crest is the highest point of a wave above the equilibrium position. And then the amplitude is how far above or below the equilibrium position that a wave stretches. So as you can see there, from the equilibrium position, you can either measure it from the middle to the trough or the middle from the crest. It really doesn't matter either way. And then the wavelength is the distance a wave travels during one cycle. So as you can see on the picture, the wavelength, you can measure it from crest to crest of the wave, or from trough to trough, or any other part of the wave where it's two similar parts of the wave. And then there are two main types of waves. The first is mechanical waves, and the second type is electromagnetic waves. Now, electromagnetic waves do not need a medium or material to travel through in order for the waves to be distributed or work. And examples of those are light, radio, and X-rays. And mechanical waves, on the other hand, must travel through a medium. And the example for this one would be sound, because we can hear sound because there's oxygen on Earth. Without oxygen on Earth, it would be a totally different story in life, and we wouldn't be able to hear anyone. And then there are also two main structures of waves. Now, the first one that I'm going to talk about to start off is transverse waves. And transverse waves are when the movement of matter is opposite to the movement of the wave, or in other terms, the vibrations of the wave. So think about a slinky, which I'll show an example over a rope. If you're moving the rope up and down, the waves start to go left to right or right to left. So the vibrations of the wave are perpendicular to the wave motion. So just think about holding a rope and moving it up and down really fast. The waves start to move left and right while your movement is up and down. And then here is an example of it.
As you can see, this is a transverse wave because the vibration of the wave moves up and down, such as the movement of my hand, which is perpendicular to the movement of energy, which is left to right. If I shake the rope once, it produces a pulse wave because only one wave or pulse is created. As I move the rope faster, it produces a periodic wave because more than one pulse is created. The energy, again, is moving left to right and is perpendicular to the wave motion, which is up and down.
Alright, and then if you didn't quite see that clearly, then here's just an animation that I found on YouTube or the internet of the transverse wave or whatever I was doing. So as you can see, first off, it's just what I did with one pulse. Now it's going to two. The faster that the hand or you shake it, the more pulses start to happen. So the faster it's going, the more pulse. And again, the wave motion is left to right, as the vibration up and down are perpendicular to the wave motion or energy, which is moving left to right. Alright, and the second main structure of the wave I want to talk to you about today is a longitudinal wave. And this happens when the movement of matter is in the same direction as the movement of the wave. In other words, particles vibrate parallel to the direction of wave motion. So as you can see in this picture, I believe of a slinky, as the movement occurs, which is, I believe it's going to the left, the particles or the movement cause the dark areas of the spring to compress, or it's called high density. And as they pass that area, as you can see where it's pointing to the rarefaction, the slinky begins to spread out, or the springs spread out before eventually returning to its original form once the wave is completely. Alright, then again, as you can see here, the vibrational movement of his hand left to right is in the same direction as the wave, or the particle movement is moving, and you can see the refraction and compressions that are occurring as it moves through the slinky. Alright, and then the last thing I want to quickly talk about is the real life example, and could be any water droplet from rain that hits lake water or anything, something like that. So as you can see, the ripple waves in a pond start or anywhere with a disturbance in water. Disturbance causes the water on the surface near that point to move, which in turn causes points farther away to move. The waves travel outward in a circular pattern, as you can see, away from the original disturbance. And then water is the medium, so this is technically a mechanical wave, and as the particles or water molecules vibrate up and down as waves pass, after waves have passed, the water returns to its original position.